Good morning, everybody. So thanks for attending. I'm AXELLE, and I'm going to talk about exactly this, those Fitbit trackers that we have for sports or fitness tracking. So, well, first, a little bit of background on wearables. I'm sure you're aware, but there's actually plenty of different wearables. More than I could actually think of. There's, of course, smartwatches. You've got also portable wearable cameras, wristbands such as these. There's plenty of different vendors for those. You've got also some more like funky stuff like Atmos skin detector, a skin exposure detector. There's even also actually a drowsing detector. So I hope this one won't be useful for my talk. Music beanie, connected T-shirts, reality augmented glasses, even connected shoes. That's not what I'm wearing today, though. And then plenty of other ones like smart helmets, which are detecting carbon, monoxide of carbon, things like those. Smart pants, smart socks, even smart bras to combat overeating. So plenty of different stuff. And today, so we're going to talk about this one, which is the Fitbit Flex. On this little tracker there, well, if I open it, which I'm going to do just right now, well, you've got, this is just the elastic plastic wristband with no intelligence inside, and everything, actually all the rest, is on there, so it's pretty small. You see it's between my two fingers there. And you've got, for there, well, an ST microelectronics microcontroller there, on which you've got an ARM CPU, an ARM Cortex. You've got also real-time clock on that microcontroller. You've got an integrated chip that will handle all the Bluetooth connection. So that's actually, in this case, the Bluetooth low energy. You also have, well, which is very important in that case, a micro electromechanical system, three-axle accelerometer, so that is what is measuring the movements, up, down, left, right, and, well, all the different axes. And, of course, then afterwards something that is handling, the battery charger, and that's about all that is on there. What's interesting in that particular case for this model Fitbit Flex is what's not on there. And what's not on there is that you don't have any altimeter and you don't have any GPS. So, how is it working? Well, everything begins with all the movements you are doing. Okay, this is how it will count the number of steps I am walking during the presentation or whenever. It will count, so walking steps, running steps. And then based on what I have entered on my user profile, that is how it will compute the distance I've been walking. I will tell it, okay, I'm this height, my gender, my age, my weight, and from that it computes all the other kind of data it needs to. So distance is basically the walking stride multiplied by the number of steps. It's pretty easy, and the walking stride is taken from my height, I guess. It also works out the number of calories I have been spending, and that is based on what they call the basal metabolic rate, BMR. They also work out the very active minutes, so this is basically when I've been walking or running very much in very short time. And all of this is computed on Fitbit servers, not on the tracker. On the tracker, you only have the walking steps and the running steps. Actually, there's also a special mode on this one, which is, the sleep mode. If you kind of tap it, like there's a special combination 5 times, it will enter the sleep mode. The sleep mode is another special mode where all the movements will be handled as if I am sleeping. So if I'm not moving at all, it will say I'm sound asleep. If I'm moving a little bit, it will say I'm restless. And if I'm moving very much, it will think that I'm actually awake. And that's how on the server, on the Fitbit server, it computes what they call the sleep efficiency, which is actually the amount of time, the ratio between the time I'm really sound asleep and the full time I'm in sleep mode. Okay? I'm sure several of you have heard about Fitbit actually several years ago because it was quite embarrassing, but they disclosed the sexual activity of plenty of users online just through a Google search because the default privacy settings for user profiles were just wide open, so anybody could just Google around and find out sexual activity of anybody. Wait, so how can we measure sexual activity with just that? I told you there was only a 3-axis accelerometer. Well, actually, that's the trick. It is not measuring any sexual activity at all. What happens is that it only measures activity. And so while it's measuring some activity, after it asks the user to go on the website and match a given activity to some very precise activity among a list. And in that list, you've got plenty of stuff. I picked up like the most amusing ones, sexual activity, cooking Indian bread on an outside stove, 211 calories per hour. Found that one great. Vacuuming, 246 calories per hour. Horse grooming, 422 calories per hour. All of these actually far less than sexual activity. Don't ask me why. Okay. And actually, there's really a very long list of those possible activities. And you just basically choose there, and that's how, in the end, well, the sexual activity of plenty of users was released publicly. This list no longer exists. What happens is that when you are doing something particular, you have to go on the website and you enter manually the activity, and you say how much calories are going to correspond to that. The good thing is that despite, well, it was really an embarrassing disclosure, Fitbit was very reactive about it, and they fixed it just the next day it was released, preventing access to all the user profiles, and also contacting the web search engines to make sure that people would no longer be able to access those former pages. So if some of you are currently trying, well, you can try. You will only get that, you will only get that placeholder page there, which says, well, you no longer are able to access that information. There are some other vulnerabilities which are actually known and no longer work. But so like 4 years ago when people were researching on that or on the Fitbit trackers, well, the security protocol for the synchronization between the tracker and the servers, well, it wasn't secured at all. So it means that I could upload to the server that I had been running like 200,000 steps. It wouldn't say, It wouldn't say anything about that. I could actually make anybody else do that running because there was no authentication, or I could eavesdrop on that and see what people were doing. Well, besides the amusing part of it, it was actually also there's a financial link because people could make profit out of it. When you run or you walk quite a lot on Fitbit, you earn badges. Those badges are just like virtual rewards that will say you've been doing well. But some companies like HIP, I don't know how it's pronounced, well, they actually give you some really financial rewards when you receive this or that badge from Fitbit. So this means that you can have, special discounts for sports shoes or things like that. So that there was, in the end, some money involved in that part of hacking. All of this no longer is no longer possible on the new Fitbit trackers, the one I have here. There are still some vulnerabilities, actually. So they aren't too nasty, but one of those was, that you can abuse the physical sensors without too many problems. And for instance, if you tie the Fitbit tracker and you tie it to a rope and you make it run, I'm trying to put it back. Anyway, just think it's there. And you turn that. So I was doing that in my office, just imagine. I think my colleagues thought I was, going nuts. And actually each spin will register one step. That's one way to do it. Also, if you shake it firmly towards the ground, that's one step. But it's as tiring, actually, as walking, so I prefer to do the walking than actually doing that. Some other researchers in 2013 had the lazy idea to tie it to the car of a wheel. So while they were going at 16 kilometers per hour, I think they registered in something like 50 steps for that average speed, basically. This is still working. I've checked. It's still working, although it's not too much of an issue, of course. The other things also, of course, that are still working is the Bluetooth sniffing part. This is a Bluetooth device, so of course, if you've got a Bluetooth sniffer, you can find it, you can see it's there, you can possibly track the user that way or not. And it's actually the way that Fitbit recommends its own users to find lost devices. They tell you, if you've lost your device, go and install on your iPhone an application called Light Blue, or on Android, it's called Bluetooth Finder, and install that, and you'll find your lost tracker. So we've got plenty of interesting vulnerabilities, but which no longer work. Some interesting vulnerabilities, but which aren't too nasty, which still do work. And that was enough for me, to want, of course, to do some more research on those new models of Fitbit trackers. It's really the usual reasons, actually, to be doing this, of course, is that while they fixed the initial issues about the synchronization protocol, for instance, they considerably locked down the whole system, which means that now, if Fitbit servers are down, your tracker is useless. It will keep the data for a few days. That's no problem with that. But let's say, unfortunately, Fitbit goes bankrupt, for instance. You can just, you can trash them. You won't be able to do anything out of it. You won't be able to register your steps anymore. It will be registered for some time, but you'll never be able to access the data. Some other reasons, obviously, is, well, that they provide support for Windows and for Macintosh, but I'm a Linux user, so, well, not good for me. Some other things also is that, well, I want to know what are, the data which are transmitted, of course. And also, actually, I'm a malware analyst. My initial concern there was really if those trackers could either get infected or be an infection vector. So, as usual, when you start research on some things like that which haven't been very much investigated, the problem is that everything is proprietary. So you don't find that much documentation. There's no real technical user documentation or even developer documentation online. This means you've got to do all the reversing. So this is why it's kind of particularly long to do, and, well, there's a lot of work. I helped myself with some very good utility written by Ben Alar. He wrote a Python utility to be able to synchronize the tracker on Linux with the dongle. And, well, it's Python code, so just reading the code is pretty interesting because you start to learn how it's working. But there's still a lot of things to do on this. So, those are the different actors that we have. So on one side, we've got the Fitbit tracker. Then, and on the middle, on the host, I'll get it for you just to show. This small thing is the dongle, the USB dongle, and Bluetooth dongle there. And, well, the tracker is going to communicate with the dongle through Bluetooth low energy, and then the dongle communicates to the Fitbit server, or the dongle or a mobile phone with Bluetooth low energy are going to communicate through HTTPS to the Fitbit servers. And on the host, where I have my USB dongle attached, well, basically you've got two different USB endpoints. One is like communication to the dongle, and the other one is communication to the tracker. So while I'm walking, running, whatever, the tracker registers a few steps. All that kind of data is on the tracker, and it gets encrypted on the tracker, right? Then it is sent over to the dongle, where the encrypted information is just encapsulated in some XML form. And the XML form is sent over here to the Fitbit servers, where it is decrypted. Now, it's really very important to understand at this point that the USB dongle, the dongle isn't doing anything at all. It is not doing any decryption or encryption. It doesn't have any keys. I've really checked this because it's an important point for reversing there. It's outside the security boundary. Everything is done on the tracker or on the Fitbit server. So, knowing this, I started reversing the messages between the tracker and the dongle. Plenty of messages, so like 16 dongle messages, 24 tracker messages. Also the communication protocol between the dongle and the Fitbit servers. What I do not have, though, as of today, is the encryption algorithm, which is between the tracker and the Fitbit servers. So I'm still looking on that. We'll discuss that point later, but it's really something I want to reverse. So, just before I show, like, you know, some about the sorry, the messages, I'm going to talk about the tools that can be used. Well, whenever you plug in the dongle on a Linux system, happens sometimes that the dongle is actually claimed by the USB human interface. If that happens, well, you've got to make sure to unclaim it so that you can use it yourself. That's pretty useful. Then you can use, so that's a utility of Ben Alar, which is called Galileo, which will actually do the synchronization. And that is also pretty useful because there's plenty of options. You can tell it, for instance, not to send the full data to the Fitbit service, but just to do the communication between the tracker and the dongle. That's all. And you can sniff that, for instance, with Wireshark or things like that. There's also an interactive mode. It's pretty cryptic. You really have to know what you want to do with it because you've got to know the messages, but still it's helpful to do some hacking. So I'll try just a demo the synchronization of my tracker here with the dongle. So it's not a live video, so oops. So I just pray it works. So actually, what I've run there, it's going to try and discover all the trackers. If there are some other trackers among you, we'll probably see it as well. So there it goes. It is discovering all the trackers which are around, found mine, and there's somebody else, 0696838D. This is not me. This is all the data. So synchronization. And also synchronizing that other person, but that didn't succeed for that one. So you've got here, where's my pointer? Yeah, there it is. Okay, so this one is mine, tracker, because it's unknown because I haven't got any specified name for that, but it's mine, and finished did the download for that one. So as I said, well, of course you can do afterwards some Wireshark to understand what are the packets which are being transmitted. You just have a look at the leftover capture data. It's always pretty useful there. And then that's basically all you actually need to do the reversing of the tracker. You can then start up to write your own Python code to talk with your tracker without any specific problem. It's pretty easy. It's like, writing to a device, reading from the device. Nothing really difficult. The only actual difficulties in that coding and that implementation is dealing with timeouts. You've got to be patient when you talk to a tracker. If you send it packets as a bulk very, very often and do not wait, well, you're not going to get the answers, and the communication won't work. So if you've got to send one packet, be patient, wait for the response. Send another packet. Sometimes, for instance, the discovery packet, well, there's a very long timeout. You've got to wait 5,000 milliseconds before you get an answer. So that's part of the difficult thing there. And this is how I started writing my fuzzer. Of course, everybody starts with a fuzzer when it's into a reverse engineering. So I fuzzed the tracker, and I kind of found that way plenty of different quirks, the fact that command identifiers, for instance, well, they're on 7 bits, not on 8 bits. I found some unknown, actually, some error codes, some commands which were actually unknown, and of course some vulnerabilities, but I'm unable to discuss those today. So let's go down into the format of packets. So this is what dongle messages look like. It's really very simple, generic format. It starts with a length for the packet, then the command identifier, and then some payload. The full packet can be of variable length. Sometimes it's padded with zeros at the end. Sometimes it is not. I don't exactly know why. And this is, for instance, a list of possible command identifiers and commands that we can send, and some of the responses that we can have from the dongle as well. I'm not going to detail all of those. That would be far too long. But for instance, let's have a look at what happens if we want to get some information from the dongle. Well, what happens is, so on the host, send a first packet to the dongle, and the first packet there, this one, yeah, so 02 is the length of the packet, 01 is the command identifier. And that gets to the dongle in here, and it responds with like 1508. 15 is in hexadecimal, so that's like, I think, 21 bytes. And 08 is the command identifier for the response. And then you have the major version of the dongle, the minor version of the dongle, the MAC address of the dongle. Okay, so pretty simple packet format. For the trackers, it's slightly different. What happens is that the message are always of a fixed length. It's 32 bytes, whatever happens, and they also have always starting by C0. And that's a list of possible message trackers that we can have, and the responses. So we'll detail all of those. No, we won't. That would be too long. But I'm sure you're actually, hopefully, interested in how I actually am, synchronizing with my tracker. So, to do the synchronization, what happens is that the first thing is that you have to make sure that you start in a clear state. I'm sorry, but I think it's my hair. It's not you, so next time I'll cut my hair before the talk. So you disconnect everything or any tracker to make sure that you start in a clear state. And then you ask for the dongle, information about the dongle that you are using. And then you start the discovery. So for the discovery, well, all the trackers which are there will actually send back some message and give the information of their MAC address, where they are. And when all the trackers have been found, well, the discovery ends, and it says, well, cancel the discovery and do something else. Then we are going to establish a link with one of those trackers. And there's plenty of messages for that. Once this is done, well, you say, okay, I've established the link. Now I've got to establish the Bluetooth link with the tracker. So now we do have actually the communication with the tracker which is set up. Now what we have to do is to get the data. So the walking back. Sorry. It looks really better. So I was saying when we established the link there, and now we have to send the data. So the data is there. It will be the walking step, the running steps, all that kind of information. So the dongle says, okay, please give me a dump of all the information, the new information you've got on the tracker. And then the tracker says, okay, I'm going to start and give you some information. And then it will send the information, the dumps, so multiple packets, depends how much information there is to transmit. And at the end, okay, I've finished, it's fine, I've dumped all that information. And you've got plenty of different dumps which are possible. So one of those is the mega dump. It's called a mega dump. So that is the walking steps, the running steps. You also have a micro dump. A micro dump is used for pairing or for updates, for instance, and also all the responses from the server. So for instance, on the Fitbit tracker, you can set an alarm. If you set an alarm, you're setting it on the Fitbit servers, and then when it will respond, what happens is that it will send in a megadump response. It will set the bytes for that specific alarm so that the tracker vibrates at the right time. Okay, and we have as well, the format for that megadump. There it goes. We have a first byte for the device type. So in my case, I've got a Fitbit Flex. So we'll start with a byte 28. Then we've got a sequence counter for bytes, which is, it's there. And then something which identifies the model of the tracker. And then starts that. And yeah, there it is. So that's for the format of the tracker. That's what it looks like. Okay, we're not going to detail that. And that encrypted blob that you saw before with, the beginning of the format, it gets encapsulated into the XML frames that go to the server. Now, of course, that's what I said, it's hack in progress. I don't know everything on that part, and this is still some open research. I don't know what is the algorithm that is used on the tracker and on Fitbit. I don't know the key either, of course. I do have a few clues, because what happens is that on the servers, on the mobile phone application, I found that, well, they were using, for instance, and referencing AES and XT very often. So it could be one of those. But when we checked the product specifications of the microcontroller, which is used on the tracker, well, it's not supporting AES. So if it's AES, which is used, well, it's not hardware accelerated. So maybe it can be as well XT, I don't know. So now some fun thing we can do with the tracker if, I don't know, the servers are no longer there. Well, playing a little bit with the various messages that we reversed just previously, we noticed that there are some authentication messages. What happens here is that the dongle will send a local random number to the tracker. The tracker will also send its own random number, and the dongle will compute a cipher-based MAC based on those two and send it to the tracker to finish up the authentication. So my idea was then, well, okay, we're going to use that tracker, but as a source of entropy. So that thing there. Okay, in cryptography, we're always looking for good sources of entropy, so I thought that would be a good idea there. To do that, what we do is we just send the first message with a dummy local random number. Actually, we don't care about that. What we care about is the response from the tracker, because the tracker is going to generate a random number. And then we never complete the authentication because we're not trying to authenticate. We're just trying to get some random numbers. And that's how we get a flow of random numbers. So I've got also a small demo for that. So that is my Python script that will send the authentication message from the dongle to the tracker, and hopefully if it works, I'll get some random bytes from the tracker. At the beginning, as you'll see, it takes a little bit of time because what happens is that it's got to do the discovery. Yeah, I hope it will work. Yeah. Oh, that's cool. It does work. So you get some random bytes there. Now, I did check. However, if the entropy of the source was good or not. And it turns out, actually, that the entropy is pretty okay. It's, well, something like 7.7 as I measured, which doesn't mean much because it's just a number, but just as a comparison, a human readable text would have an entropy around 3 and 4, and a heavily encrypted script with text with AES will have like something like 7.8, perhaps 7.9. I also computed actually the entropy of dev random or dev random on Linux, on Linux boxes, and it was just like slightly above 7.7. So it's maybe not the best entropy source, but it's quite okay. I also wondered if while I was walking, maybe the entropy source would get a little bit better because it would induce some more entropy on the device, but actually it did not change anything. So I guess it's not getting its entropy from the accelerometer. And that's about all. So there's still plenty of research to do on that tracker. As you know, I've listed a few things I want to have work on there. There are a few LEDs, for instance, on the tracker, and I'd love to, have them blink the way I want, or have the tracker vibrate whatever way would be useful. There's still some fuzzing I have to do on the dongle as well. And of course, there's also that issue about the encryption, which is really something I have to do. As for now, I'm open to plenty of ideas if you have some. I think there's no other solution than like opening the box and having a look at the hardware level to see what actually that piece of hardware is really computing. Thanks, and if there are questions.
Good. Were you able to find some kind of update command in the control? The protocol you have reversed. Like, is it possible to update the firmware running on the STM32 something?
So yes, there are some updates which are sent. They are sent in those famous mini dumps. The problem is for me that they are sent encrypted. The payload is encrypted, so I don't know exactly what is being sent, if it is like some firmware update for the microcontroller or like a little bit higher level or not. This I can only do once I know what is the encryption algorithm. But yes, there is in the full protocol, it's called mini dump. That's where all the updates come and go. Well, thanks.